Okay, in this part, we are going to learn about aviation, high altitude, and space physiology. So, aeronautical advancements have made it increasingly more important to understand the effects of altitude and low gas pressures, as well as other factors, acceleratory forces, weightlessness on human body. So today, our age is space age, okay? You all know Elon Musk, right? You know him. Uh, he's inventing, making new spacecrafts to go to Mars or something. He's a crazy man, okay? Uh, so what happens when we go to the space? In this lecture, we are going to learn about it. So we all traveled by plane, right? We plane, the plane flies in 10,000 feet, 10,000 meters high. Uh, so very low oxygen partial pressure is present. So how come we can succeed to do it? So we are going to learn some information about them in this lecture. Our topics, main topics are effects of low oxygen pressure on our body and the weightlessness. What kinds of effects due to weightlessness in the space? If you stay in the moon for a while or in space stations, then what happens to your body? Especially gravity is not that high, so you will lose some of your bones, calcium stores of your bones. So osteoporosis definitely develops in astronauts, okay? And their muscles will be no more strong. When they are back to the earth, they can't stand even in the first days in the world. All right. Now, effects of low oxygen pressure on the body. A decrease in barometric pressure is the basic cause of high altitude hypoxia. So when we look at the table, we will see that altitude increases, the barometric pressure decreases, and oxygen partial pressure decreases proportionately. So the alveolar oxygen partial pressure will also be reduced by carbon dioxide and water vapor. So this table we will see a few times during this presentation, I guess 2 times at least. So in low oxygen atmosphere in high altitude, you see here this is the sea level, okay? 760 millimeter mercury barometric pressure. 20% of air is made of oxygen. So oxygen partial pressure in the air is 159 millimeter mercury. In the alveoli, the concentrations of carbon dioxide, oxygen, and arterial oxygen saturation, you can see here. Although oxygen concentration is 159, as you see, the oxygen concentration in the alveoli decreases to 104. Why? Because of water vapor. Water vapor, 47 millimeter mercury, water pressure. Okay, and then there is carbon dioxide coming from the tissues by venous blood to the lungs continuously, and then its concentration is 40 millimeter mercury, and its concentration is almost zero in the air. Okay, and saturation of oxygen is 97%. If we breathe pure oxygen, in this case, you see the oxygen concentration in the alveoli. Instead of 104, 673, and carbon dioxide is the same, and arterial oxygen saturation is 100%. If we go to up 10,000 feet or 3,000 meters up, then see the pressures, what happens to them. If we breathe air, okay, as you see, oxygen in the air will go down. Total air pressure will go down. If we go to the mountains, for example, 3,000 feet, Erzurum, the altitude of Erzurum is 2,000 feet, 2,000 meters almost, 1,800 something, okay? So this is 3,000. So air pressure goes down, and then oxygen partial pressure in the air goes down from 159 to 110. So in Erzurum, it is somewhere between these, okay? So oxygen in the alveoli will be decreased, as you see, 67 millimeter mercury, unacclimatized person, and 77 is acclimatized or adapted, accommodated, okay? Person. Staying in this environment for a long time causes accommodation, acclimatization, it is called. Carbon dioxide concentration goes down to 36. In acclimatized person, it is less, 23 millimeter mercury, and arterial oxygen saturation is 90. In acclimatized person, it is only 92, only 2% higher. How about pure oxygen breathing? If we respirate using pure oxygen, you can see you have 100% oxygen saturation, and then carbon dioxide is the same. How about 20 feet, 20,000 feet altitude, or 6,000 meters high? So this is very, very high mountains, okay? Like Everest or something. As you see here, barometric pressure goes down from 760 to 350 almost, and then oxygen in the air, oxygen partial pressure in the air goes down from 160 to about 70, and then oxygen partial pressure in the alveoli is only 40 millimeter mercury now. In acclimatized adapted person, it is 53, and saturation is 73%. On the other hand, in acclimatized person, it is 85%. It's quite high. And then oxygen level, carbon dioxide concentration goes down to 24. In acclimatized, it is 10. Again, if you breathe using pure oxygen, you have 100% oxygen saturation, and carbon dioxide is normal value. So as you see, the importance of breathing pure oxygen in high altitude, okay? In airplanes, they have pressurized cabin, and then we breathe, I think, air rich in oxygen. 30,000 meter high, it is about 9,000 meters high altitude, and then as you see, this time oxygen level, partial pressure goes to very, very low values now, and oxygen saturation is very, very low, only 24%, and oxygen in alveoli is 18, and in acclimatized people it is 30, and then as you see, carbon dioxide concentration does not change much. But if you again breathe 100% pure oxygen, then you get 99% of oxygen saturation. So in high altitude, carbon dioxide concentration goes down. Why? Because you start to respirate deeply and frequently, okay? Due to decreased oxygen saturation in the blood this time, this will cause carbon dioxide level to fall. So to low altitudes, to low In high altitudes, carbon dioxide concentration will go down. In acclimatized person with a 5-fold increase in ventilation, blood carbon dioxide concentration can be as low as 7 millimeter mercury because of increased ventilation. What happens then if carbon dioxide concentration goes down? Or carbon dioxide is a toxic gas, and we are already sending it out by our expiration. It can be low. It's okay for us, you can think, but it's not that case, because carbon dioxide is required to stimulate respiration. We have learned about the regulation of respiration subject that carbon dioxide can cross blood-brain barrier and can enter the brain and then stimulate respiration, right? So when it goes to very low values, then respiration can be inhibited, okay? And you know, when carbon dioxide concentration goes down, what happens in the body? In terms of acid-base balance. When you lose carbon dioxide, you lose acid, okay? In your body, there will be base excess in this case, and then alkalosis. The pH of the blood will go up, and hydrogen concentration will go down, and there will be alkalosis in the body. Kidney take part in these conditions, and then in these alkalosis conditions, then your kidneys will lose bicarbonate and will try to save hydrogen, okay, to counteract this acid-base imbalance. Increased alkaline or decreased acidic conditions, in this case our kidneys tries to save hydrogen and then to lose bicarbonate to compensate hyperventilation and loss of carbon dioxide due to hyperventilation in high altitude. All right, water vapor pressure in the alveoli, it remains at 47 millimeter mercury as long as the body temperature is normal, regardless of altitude, okay? Water vapor, when we are breathing now, we have water vapor. The air we inspire, it goes to the nostrils via our nose. We have concha, and then these conchae inside of the nose will humidify the air, will clean, will filter the large particles in the air, and then it will reach your deep parts of the alveoli, okay? So water vapor is 47 millimeter mercury, and we lose about 500 milliliters of water via this evaporation, this insensible loss of water we are not aware of. That's why when we are calculating how much fluid is entered and how much fluid is gone away from the body, we add 500 more because we cannot measure it. We can measure the urine volume, but we cannot measure the evaporated water, okay, lost by respiration. Okay, carbon dioxide and water vapor pressure reduce the alveolar oxygen, okay. Barometric pressure is 253 millimeter mercury at top of 29,000 foot, meaning 9,144 meters, like Mount Everest. 47 millimeter mercury of this must be water vapor, leaving 206 millimeter mercury for the other cases. In acclimatized person, 7 millimeter of 206 millimeter mercury must be carbon dioxide, so the rest is 199 millimeter mercury. If there were no use of oxygen by the body, 1/5 of this would be oxygen, 4/5 would be nitrogen, so the oxygen alveoli, in the alveoli would be 40 millimeter mercury around. However, some of this alveolar oxygen is normally absorbed by the blood, leaving the alveolar oxygen about 35 millimeter mercury in this high, in Mount Everest, 9,000 meters high. Breathing pure oxygen increases arterial oxygen saturation. Yes, we have seen it in the table. We have just analyzed, examined the values. Up to an altitude of about 10,000 feet, I mean 3,000 meters, the arterial oxygen saturation remains at least as high as 90%. It falls progressively until it is only about 70% at 20,000 feet or 6,000 meters, and much less at still higher altitudes. Okay, we have just seen this table. Now, breathing pure oxygen. When we breathe pure oxygen, then the space in the alveoli formerly occupied by nitrogen becomes occupied by oxygen. At 9,000 meters in Mount Everest, for example, aviators could have an alveolar oxygen partial pressure as high as 139 millimeter mercury instead of 18 millimeter mercury they would have when they breathe air, normal atmospheric air. Okay, you see here the altitude, thousands of feet. If you breathe air, and then arterial oxygen saturation you can see here, and then if you breathe pure air, the oxygen saturation will be very high until 30,000 feet. 30,000 feet. Okay, what was in the in the Mount Everest? 9,000 or 30,000. Yes, in the Mount Everest. Okay. Otherwise, would be very, very low value. So you cannot climb Mount Everest without support of pure oxygen. Okay. A person remaining at high altitudes for days, weeks, or years becomes more and more acclimatized to the low oxygen partial pressure. Acclimatization makes it possible for a person to work harder without hypoxic effects or to ascend to still higher altitudes. So the principal means by which acclimatization comes about are the following. First, pulmonary ventilation will be increased. Red blood cell amount in the blood will be increased. Diffusing capacity of the lungs will be increased. The vascularity of the tissues will be increased, so there will be new blood vessel formation or angiogenesis. And also the ability of the cells to use oxygen, the oxidative enzymes, the activities of them will be increased. Now, pulmonary ventilation can increase 5 times in the acclimatized person, but only 65% in the unacclimatized person. So acute exposure to hypoxic environment increases the alveolar ventilation to a maximum of about 65% above normal. If the person remains at a very high altitude for several days, the ventilation gradually increases to an average of about 5 times of normal. Now, acute increase in pulmonary ventilation. When you are exposed to low oxygen partial pressure, then peripheral chemoreceptors will be stimulated, and then they will stimulate center of respiration in this way, and then pulmonary ventilation will be increased 65%, so that in this case we will expire more carbon dioxide. This time carbon dioxide concentration will go down, and then pH of the blood will go up, or this is alkalosis. Both of them will inhibit respiratory center, thereby opposing the effect of low oxygen partial pressure to stimulate the peripheral respiratory chemoreceptors in the carotid and aortic bodies. The chronic increase in pulmonary ventilation. The acute inhibition fades away within 2 to 5 days. So in the beginning, due to hypoxia, respiration will be increased, but this time due to hypocapnia, respiration will be inhibited, but this inhibition will go away after 2-3 days, allowing the respiratory center to respond with full force, increasing ventilation by about 5 times of normal. The decreased inhibition results from reduction in bicarbonate ion concentration in the cerebrospinal fluid and the brain tissue. Our kidneys starts to lose, not reabsorb bicarbonate, and then bicarbonate concentration goes down in the brain, so that inhibition of the respiratory center will go away. This in turn decreases the pH in the fluids surrounding the chemosensitive neurons of the respiratory center, thereby increasing the activity of the center. Now hematocrit and blood volume decrease during acclimatization. Hypoxia is the principal stimulus for an increased red blood cell production. With full acclimatization to low oxygen, the hematocrit rises from a normal value of 40-45% to 60 or more percent. In addition, blood volume increases often by 20% to 30%, resulting in total rise in circulating hemoglobin of 50% or more. This increase in hemoglobin and blood volume begins after 2 weeks, reaching half development within a month or so, and full development only after many months staying in high altitude. So pulmonary diffusing capacity can increase as much as 3-fold after acclimatization. Normal diffusing capacity for the oxygen through the pulmonary membrane is about 21 milliliters per millimeter mercury in a minute. The following factors contribute to 3-fold increase after acclimatization are increased pulmonary capillary blood volume, so expands the capillaries and increases the surface area through which oxygen can diffuse. Increased lung volume expands the surface area of the alveolar membrane. Increased pulmonary arterial pressure forces blood into greater numbers of alveolar capillaries, especially in the upper parts of the lungs, which are poorly perfused under usual conditions. Zone 2, which will be opened only during systolic phase normally. Now they are fully opened, so they are converted to zone 3 blood flow region. Chronic hypoxia increases the number of capillaries in some tissues. Cardiac output often increases as much as 30% immediately after a person ascends to high altitude, but then decreases toward normal as the blood hematocrit increases. Thus, the amount of oxygen transported to the tissues remains about normal. The number of capillaries in some tissues increases, especially in animals born and bred or grown at this high altitudes. The greater capillarity is especially marked in tissues in which vasculature has mainly a nutritive function, not kidney. Kidney vascularity is the same because it is functional, it's not a nutritive function. So hypoxia inducible factor, a master switch for the body's response to hypoxia. Hypoxia inducible factors are DNA binding transcription factors that respond to decreased oxygen availability and activate several genes encoding proteins needed for adequate oxygen delivery and use of it for the energy metabolism. Hypoxia inducible factors are found in virtually all oxygen breathing species, ranging from primitive worms to human beings. Some of the genes controlled by hypoxia-inducible factors, especially HIF1, include the following: genes associated with vascular endothelial growth factor, which stimulate angiogenesis; erythropoietin genes that stimulate red blood cell production; mitochondrial genes involved with energy utilization; glycolytic enzyme genes involved with anaerobic metabolism; genes that increase availability of nitric oxide, which causes pulmonary vasodilation; So, in the presence of adequate oxygen, the subunits of hypoxia-inducible factor required to activate various genes are downregulated and inactivated by specific hypoxia-inducible factor hydroxylases. In hypoxia, the hypoxia-inducible factor hydrolases are themselves inactive, allowing the formation of a transcriptionally active hypoxia-inducible factor complex. Thus, the hypoxia-inducible factors serve as a master switch that permits the body to respond appropriately to the hypoxia. So the scientists inventing this hypoxia-inducible factor for the erythropoietin formation in hypoxic conditions, they got the Nobel Prize a few years ago. A person who remains at high altitude too long can develop chronic mountain sickness, okay? There will be vasodilation in the brain tissue. There will be pulmonary edema development. So it is acute mountain sickness. And then if the person stays in the high altitude for a long time, what will happen in the body? Red blood cell mass and hematocrit become exceptionally high. The pulmonary arterial pressure increases even more than normal. The right side of the heart becomes greatly enlarged, and the peripheral arterial pressure begins to fall. Congestive heart failure will follow, and then death often follows unless the person is removed to a lower altitude. So the person should climb gradually, okay, slowly. And if he or she develops mountain sickness signs, and then he or she should be taken lower altitudes immediately. Otherwise, brain edema and pulmonary edema can cause the death of the person. Viscosity of the blood is increased quite much, and it is very difficult now to pump this blood, okay? And pulmonary artery pressure is increased very much, and right ventricle will fail, will not be able to pump blood against this increased pressure. This is called cor pulmonale, you know, in medicine, and then there will be cyanosis development in the patient. Okay. When a child grows in high altitude, then also the chest cavity of that person will be enlarged. Not only the red blood cell amount, but there will be physical, anatomical adaptation, okay? When these children come to sea level later on, their anatomical structure, enlarged barrel-shaped chest will not change, okay? Their red blood cell amount can go down, but barrel-shaped chest cavity will not change. Again, the same when somebody goes up very high altitudes, his chest size does not change, okay? You can see here the difference between mountain dwellers and sea level dwellers. Although they spend time in high altitude, they cannot reach the mountain dwellers, okay? The quantity of oxygen in the blood is very high in mountain dwellers compared with the sea level dwellers, even when they are accustomed to acclimatized, okay? Reduced work capacity at high altitudes and positive effect of acclimatization. So in addition to mental depression caused by hypoxia, working capacity of muscles and the cardiac and skeletal muscles is greatly decreased in the state of hypoxia. In general, work capacity is reduced in direct proportion to the decrease in maximum rate of oxygen uptake that the body can achieve. To give an idea of the importance of acclimatization in increasing work capacity, consider the large differences in work capacities as a percentage of normal for unacclimatized and acclimatized people at an altitude of 17,000 feet. So in this figure, you see the working capacity in unacclimatized person going 17,000 feet upwards. then working capacity goes down to 50%. When this person stays there for 2 months, it increases to 68%. But it is 87% in people living in dwellers in high altitudes, okay? Thus, naturally acclimatized native persons can achieve a daily work output, even at high altitude, almost equal to that of a lowlander at sea level. But even well acclimatized lowlanders can almost never achieve this high 87%, although they increase it from 50 to 68%, okay? Now finally, weightlessness in space. Physiological problems exist with weightlessness. Most of the problems that occur appear to be related to three effects of weightlessness: motion sickness during first few days of travel, translocation of fluids in the body because of failure of gravity to cause normal hydrostatic pressure gradients, and diminished physical activity because no strength of muscle contraction is required to oppose the force of gravity. Physiological consequences of prolonged periods in space are decreased blood volume, decreased red blood cell mass, decreased muscle strength and work capacity, decreased maximum cardiac output, and loss of calcium and phosphate from the bones, and loss of bone mass or development of osteoporosis. The physiological consequences of prolonged weightlessness are similar to those experienced by people who lie in bed for an extended time. For this reason, extensive exercise programs are carried out during prolonged space missions, and most of the effects mentioned are greatly reduced, except for some bone loss. So in space, spacecrafts, there are centrifuges applying gravity to gravity, some, although not that much, being on Earth, but still prevents these changes in the body. In previous space expeditions in which the exercise program had been less vigorous, astronauts had severely decreased work capacities for the first few days after returning to the Earth. They also had a tendency to faint when they stood up during the first day or so after return to gravity because of their diminished blood volume and perhaps diminished responses of the acute arterial pressure controlling mechanisms we have learned earlier. Okay, when you wake up in the morning and then blood volume will not be able to fill, so sympathetic activity should be increased quickly. Blood vessels should be constricted and the heart should pump the blood stronger, but there is not enough volume, so they can faint. They have orthostatic hypotension. Even with an exercise program, fainting continues to be a problem after prolonged weightlessness. Okay, I think that's all for space physiology. In high altitude, the problem is decreased oxygen concentration, and due to hypoxia, respiration will be stimulated. This time we will lose carbon dioxide, and the carbon dioxide concentration goes down, and decreased carbon dioxide concentration will inhibit respiration this time. So it takes time for the adaptation. Now kidneys will not reabsorb bicarbonate, or we start to excrete high amount of bicarbonate, so that bicarbonate concentration goes down. This means the hydrogen will be increased. Okay, there is acid-base balance in the body. If you lose base, then acidosis will happen. So inhibition due to alkalosis will be decreased on the respiratory center, in the chemosensitive areas in the brainstem, so that respiration will not be that much inhibited due to hypocapnia. Okay, so that respiration, ventilation can increase much more. We can use pure oxygen due to decreased oxygen partial pressure. If we breathe normal air in high altitude, we cannot get high oxygen saturation in our blood, and it's not good, okay? So we have to use pressurized cabins, we have to use high oxygen, pure oxygen to breathe. In the space, the problem is weightlessness, okay? There is no gravity, so calcium will be released from the bones and our muscles will be weak. Blood volume will go down, red blood cell amount will go down. When these astronauts are returning back to the Earth, then they can't even get on, okay? They can't stand very well. They can faint, their blood pressure goes down very quickly, they have orthostatic hypotension. So it takes time for them to adapt to the Earth. So to prevent this, astronauts can use centrifuges in these spacecrafts, applying a little bit gravity on their body, simulating the Earth conditions. That's all. If you have questions regarding with high altitude physiology, you can ask your questions. All right. Any questions, please? I can read on the screen or on WhatsApp also. Okay, any questions? Do you have any questions? Are you there? Is there anybody listening to me or no?
Buradayız hocam.
Evet. Any questions? Do you have any questions? Herhangi bir soru var mı? Anlaşılmayan bir yer var mı? Evet çocuklar, bekliyorum. Bir sorunuz var mı? Yani her şeyi anladınız mı? Her şey çok mu açık? Yani is it clear? Was it clear? You understood everything? Evet Yağmur, benim yok. Abdin, benim yok. Evet Abdin, biraz konuşsana ya. Azerbaycan dilinde biraz konuşur musun? Nasıl oldu şimdi, barış oldu mu Ermenistan'la? Abdin. Maybe I stop recording and then we can talk.